Okay, so we're going to find the triple integral of this function over this region using spherical coordinates. If you remember, actually we have computed this before, but I had used cylindrical coordinates. So remember that the region that I'm talking about was about the one determined by the cone. So the cone was of infinite size. It would keep increasing indefinitely. So you have to cut it somewhere. We cut it at z equals 1 last time. So, and we were integrating the height function, z, or just like this function. And we found that that was pi over 4. Now what we want to do is show this again, but from the point of view of spherical coordinates. Now, if you remember the idea, let's write what the spherical coordinates are supposed to be at a point. So they're specified by the distance from the origin, which is rho, and then this angle that I'm calling phi, and the other angle, which is theta, the same theta as before. So the change of variables was rho cosine of phi, and then rho sine of phi, sine of theta, rho sine of phi, cosine of theta. So basically y is the one that has the two signs, and everything else, and everything has a rho. Okay, now the dv in this case, remember, is rho squared sine of phi, d rho d phi d theta. Okay, and so the point is that notice that in the same way as with cylindrical coordinates, we still have one of the, in cylindrical coordinates we had one angle, in spherical coordinates we have two angles, but one of the angles is the same. So theta is still theta in both cylindrical and spherical coordinates. So we for this problem we had used the fact that like the figure was symmetric about the z-axis, right? You could rotate it and you would not see any difference. And so we can still take advantage of that. So when you look at a cross section of this figure, right? The cross section of this figure, this was like the z-axis, remember? This was like a generic axis when you cut it with the plane. You can call this r-axis or whatever, it doesn't really matter. The point is that the cross section was like a triangle, right? Because if you took this region and rotated by 2 pi, then you recover the volumetric region that's on the left hand side. And so this is the equation, the region that we were interested in. Now we just need to express it using spherical coordinates. So let's try to think about that. The triple integral that we're going to do is the following. So c gets replaced with rho cosine of phi. And dv gets replaced with rho squared sine of phi d rho d phi d theta. And again, the first integral that we're going to do is this one, and then we're going to do this one. The last one is with respect to theta, Theta, since it's the last integral, is the easiest to fill in first, because theta, for this one you can only put the two numbers, which have to be the largest and smallest value that theta takes in this region. So you needed like two pi angles, 2 pi radians to rotate the entire figure. You can say that theta goes from 0 to 2 pi. Okay. Now let's try to find this the bounds for this for rho first. So again, the bounds for rho, when you do this integral on the inside, that means that you are only letting rho change, and phi has been fixed. Remember that phi, right? Phi starts from the z-axis, so it's 0 at the z-axis, and it keeps going down. So when you fix phi, right? Fixing phi is like fixing an angle here. Okay? And so notice that for this fixed angle of phi, right, let's just fix it here. The rho is basically the distance from the origin. So rho is just going to be measuring the distance from a point on this segment to the origin. So obviously it's going to be changing because the distance from the points to the origin are not the same. So the idea is like you think of this as a axial arrow, or a radial arrow rather, which starts at the origin, right? Because the arrows all start at 0, they start at the origin, and they all hit the top, right? Regardless of which arrow you choose, like if you had chosen another radial arrow, it would also have left the region through the top. So we need to find the equation of this this top was c equals 1, right? But the problem is that you cannot put here like c equals 1, because now we are not working with cylindrical coordinates, we're working with spherical coordinates. So you have to find out what c equals 1 is in spherical coordinates. Well, but c equals rho cosine of phi. So that means that rho cosine of phi has to be 1, and that allows you to solve for rho. So you can say that rho equals 1 over cosine of phi. And so the bound that we're going to put here is we're integrating from 0 up to rho equals 1 over cosine of phi. And notice that that makes sense, because what that is saying is when phi equals 0, right? When phi equals 0, you're along the z-axis, and that gives you rho equals 1 over cosine of 0, which is 1. So that means that along the z-axis, the arrow exits through a height 1. But as you move away from the z-axis, actually the arrows take a bit more time or more length to exit the region. So the point is that these places have these segments have different radii. They all exit at the same height, but the length of the segment is different. That's what I was trying to say. And so phi, what would the phi be? Well, it's all the angles that you need in order to sweep out this region. So you start with phi equals 0 because you start from the z-axis, and then you end up on this line. Remember that this line corresponds to, let's think this out a little bit. So this was a line corresponding to the equation c equals x squared plus y squared, which again we are not working in cylindrical coordinates, so we have to ask what is c equals x squared plus y squared in spherical coordinates? Well, again, c equals rho cosine of phi. And x squared equals rho squared sine squared cosine square of theta. So sine square of phi cosine square of theta. And y equals rho squared sine square of phi cosine square of theta. Okay? And so what you can do is notice that both terms have rho squared sine squared here. So you can factorize this, and that gives you rho cosine of phi equals the root of rho squared sine square of phi times here when I squared, I should have written sine squared as on this side. So the point is that you can factorize these two terms, and so you just get cosine plus sine squared. You get cosine squared plus sine squared, which is just 1. And so you have to take the square root of rho squared sine squared, and that just gives you rho sine of phi. So you have rho on both sides, and that tells you that that cosine equals sine of phi, cosine of phi equals sine of phi, and so phi has to be pi over 4. So what that means is that these angles started as 0, and in order to reach this last segment, you have to go down by an angle of pi over 4. So the bounds here are from 0 to pi over 4. Okay? And so again, we have to get pi over 4 as the final answer. And so the integral that we must do is this one. We have to integrate from 0 to 2 pi, from 0 to pi over 4, from 0 to 1 over cosine of phi of rho cubed cosine of phi sine of phi d rho d phi d theta. And so the first integral is with respect to rho. That just gives you rho to the 4 over 4. So you get 1 over 4 times 0 to 2 pi, 0 pi over 4 of rho to the, well, you still have cosine of phi, sine of phi, times rho to the 4. Notice that there was a 1/4, which I already pulled out. And so you're evaluating this over 1 over cosine and 0, and then you're integrating against phi and theta. And so this gives you 1/4 times the integral from 0 to 2 pi, the integral from 0 to pi over 4. And so you get, when you do rho to the 4th power, you get 1 over cosine to the 4 phi, but there's a cosine upstairs in the numerator, so you get sine of phi over cosine cubed of phi d phi d theta. Okay, and now how would you do that integral? You would make a substitution. So if you make u equals cosine of phi, then du equals minus sine of phi d phi. Let's just do the indefinite integral if you prefer. So sine of phi over cosine cubed of phi d phi is just really minus u to the negative 3 d phi, which is minus u to the negative 2 over negative 2. Okay, and so that gives you the negatives cancel, so it gives you 1 over 2 u squared, but u squared would be cosine squared. So this integral really becomes a 1/4 times the integral from 0 to 2 pi of what? Of this integral, which is again 1/2 1 over 2 cosine square of phi, where phi is evaluated at pi over 4 and phi is evaluated at 0, times the theta. And then, let's see, hopefully I'm not getting any signs incorrectly. Let's see. Okay, I think we're okay so far, but yeah, I think this is fine. So this equals at 1 over 8, the integral from 0 to 2 pi. So you get 1 over cosine square of pi over 4. Cosine of pi over 4 is 1 over root of 2. So when you square it, you get 1/2, and then so you get 1 over 1/2 minus 1 the theta. Right, because cosine of 0 is 1, so 1 over 1 is 1. So what you get here is 1 over 8. So this becomes 2 minus 1, so it just gives you 1. So this is the integral from 0 to 2 pi times the theta, and this gets multiplied by 2 pi, so you get pi over 4. Which is, remember what we found using cylindrical coordinates.